Okay, so is the screen visible to you, and anyone can unmute themselves and then just correspond?
Yes, sir.
Yes,
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 sir.
sir.
Okay, good. So in this session, this is week 5 of this course. I'll be solving the assignment solutions, assignment questions, and today we have assignment 5. So the first question is, which of the following statements is correct? And we have the first given option is effective mass is independent of the shape of energy band. Effective mass is, so in context of effective mass, we can write effective mass as follows. Effective mass is related to the curvature of energy band. This term here, the second derivative of a function, is its curvature. So this is curvature of energy band, and therefore this curvature of energy band is related to the shape of it. And effective mass is independent of the shape. That is a wrong statement, because it is directly and intimately related to the shape. Then we have effective mass is small for a narrow. Now to understand this, one should understand curvature. Now curvature, suppose I have a function and function goes like this way, show in this color, and I'll draw one more function in blue color whose variation is in this way. Okay, now for this function, now if you follow this function below down this path, the tangent at this point changes very rapidly. The tangent changes its direction very rapidly, so this curvature is very large here. Is large, and for a function which is shown over here in blue, the tangent changes its direction very slowly. So we say that the curvature, that is the first derivative of the tangent, curvature, is small. Now another name I can give for this function is a very wide function. I can call it wide band. Wide band. And a function which changes very rapidly, I can call it a narrow band. So for a narrow band, curvature is large, and effective mass is inversely proportional to the curvature. So if curvature is large, effective mass would be low. So for a narrow band, effective mass would be low. For a narrow valley band, effective mass is small, and for a wide valley band, curvature is small, and curvature is related to mass as inverse, so curvature is effective mass would be large. So correct option would be B. On the same terms, we can solve the second question. Assume that the question is, given a EK relationship to us is E is equal to a k square plus constant plus some constant term, the cyclotron resonance for electrons in a field of magnitude of field given to us is 0.1 Weber per meter square. Angular frequency omega c given to us is 10 to the power 11 into 1.8 radian per second, and we are required to find the value of A in this empirical energy relation. So now from above equation, we know that effective mass is inversely proportional to the curvature or the second derivative of energy with respect to k. In such a fashion, we can write here that again 1 by h cross square del 2E by del k2. Now first derivative of E would be 2ak, and second derivative would be k, it would be gone. So second derivative of the function is 2a. Plug this value here. Let me take an additional page here. So 1 by m star would be equal to 2a by h cross square. Now omega c, that is the cyclotron frequency, is related to is as follows: omega c equal to E B by m star. One can rearrange this equation as 1 by m star would be omega c by EB. This equation and this equation one can equate. Omega c by EB is equal to 2a by h cross square. We can solve for a here. A would be h cross square multiplied by omega c divided by twice of E and B. The values of all these parameters are known to us. H cross, if one finds out h cross is h by 2 pi and its value is 1.05 into 10 raised to the power minus 34 joule second. So we will use this value. So 1.05 multiplied by 10 to the power minus 34 square multiplied by omega c given to us is 1.8 into 10 to the power 11. 1.8 into 10 to the power 11 divided by twice. Charge on an electron is 1.6 10 to the power minus 19 and magnetic field is 0.1. We can collect the 10 powers separately. 1.05 square multiplied by 10 to the power minus 68, 34 into 2, multiplied by 1.8 into 10 to the power 11 divided by 16 2 is 3.2 and 0.1 will be 0.32 multiplied by 10 to the power minus 19. Minus 19 goes into the numerator, becomes plus 19, and plus 19 connected with 10 to the power 11 becomes 10 to the power 30 plus, and 10 to the minus 68 and plus 30 gives me 10 to the minus 38 as the scientific exponent. What we are remained with is 1.05 square in the numerator multiplied by 1.8 divided by 0.32 multiplied. If you figure out this, do a small calculation, one finds it to be 6.18 into 10 to the power minus 38 joule meter square. One can round it off to 6.2 as well, joule per meter square. So 6.2 into 10 to the minus 38, 6.2 into 10 to the minus 38 would be the correct answer. Now K, the other question is K dot P perturbation term in the crystal Hamiltonian arises because now K dot P perturbation method is used to calculate the effective mass of electrons in a solid, and in that perspective we use the property that atoms are arranged in a periodic potential, and therefore V of R plus Rn is V of R. Therefore this periodicity of the potential is a necessary condition that we use in Kp perturbation method, and therefore the correct option would be because of the periodicity of the potential that this perturbation term arises. And also according to this, if one goes further to the fourth question, that according to this Kp perturbation calculation, the effective mass of a solid, now I'll write down the expression for this Kp perturbation. Just hold on. Okay. Now in real systems, what we have the expression for effective mass is as follows: is del Ki del Kj, whereas I and J are indices corresponding to x, y and z direction of the real material. Now this mass is actually a second rank tensor, okay, and its sign depends upon the derivative of the direction of the curvature. It is positive for a convex shape and negative for a concave shape, because if the shape is this, then curvature is positive, and if the shape of energy band is above, then curvature is negative. So magnitude, the direction of, or I should say sign of effective mass depends upon this curvature, and it is a second rank tensor. So what we have is option number 5, that effective mass of a solid is a second rank tensor with components of either sign. Now question number 5 is a crystal Hamiltonian has periodicity of the lattice. This is the condition given to us, and what we are required is then what is the true for Hamiltonian matrix element KH K prime. Now to know this, I will write down now given condition to us is that Hamiltonian has got the periodicity of the lattice, right, because of the potential. So if one writes down this matrix element K prime, okay, whereas this matrix element, this Hamiltonian is itself periodic because of the potential, one can write crystal potential as XH or whatever, and if I move it by a direct lattice translation, I would get the original Hamiltonian. Now I am talking about the real space. Okay. Now I can write this X crystal Hamiltonian, this XH as follows: psi k summation over this Now if I solve this matrix element, I get the following condition, where Km is a reciprocal lattice translation vector. Okay, so this is this condition says that the wave vectors K and K prime are connected by a reciprocal lattice vector, then the matrix element goes to 0, because if this condition is true, then delta function goes as 0. So what we have, so this condition is true in essence. The delta function says that if the two things, the k minus k prime, if not equal to km, then delta goes to 0. Matrix element will not be 0. Let me just correct it, because if delta, that is the definition of delta function. So if one uses this definition, then what we have is non-zero only for k equal to k prime. That is not the correct statement. The rows of matrix are also normal. No, is non-zero. The matrix element is non-zero if the wave vectors k and k prime are related by reciprocal lattice translation vector, because if k and k prime are not equal, just a second. Oh, all right. Let me just. There was a little mistake that I did. Okay. So this condition is in fact true, that if the wave vectors k and k prime are connected by a reciprocal lattice vector, then the element goes to 0. And if not, then element, the matrix element in fact, stays non-zero, right? So it's non-zero if they're related by reciprocal translation vector. Right now, okay, I would agree to this point that right now this problem is bit ambiguous to me itself. I would come to this problem in a later stage, probably when we will meet the next time for the next week, because I have to check it again. Okay, for the time being, bear this with me. I'll recheck it and would clarify this particular problem of week 5 and question 5 in the later stage. Okay, because I'm a little bit confused about the two conditions, that whether it will be non-zero, because by definition I bit of messed it up right now, but I'll clarify for sure in the next meet when we'll come next week. I'll just keep in mind that this problem is due to be solved. For right now, I'll move to the next problem. Okay, so it says that if no symmetry is utilized for a crystal of n hydrogen atoms, right? Then in a simple cubic lattice with one orbital per atom. So we have n hydrogen atoms in a simple cubic lattice with one orbital per hydrogen atom. The order of the Hamiltonian in the time binding basis would be. So if we have n hydrogen atoms, then the Hamiltonian matrix element matrix would be of, say, n hydrogen atoms would have, we will have matrix element in rows would have, there would be n rows and n columns as well, n columns and n rows, this thing, and the size of this matrix would be n cross n. So the order of the Hamiltonian matrix of this would be n cross n. Okay. Next we have is, if in the following problem, if one exploits the translation symmetry to obtain the eigenvalues of the Hamiltonian in the above problem, because this problem can become very large if n turns out to be the order of 10 to the power 23, that is the Avogadro number, then solving this matrix would be extremely difficult. Now if one uses the symmetry of the Brillouin zone, that is the translation symmetry, then the order of the Hamiltonian at each point in Brillouin zone, that boils down to only 1 cross 1. Okay, that turns out to be 1 cross 1, because it simplifies the problem to the extent that the n rows and n columns are just replaced by one matrix element. Then it's the following question we have is the reciprocal lattice of a simple cubic lattice is. Now this particular question is a repeat question which we have already solved in our earlier questions. For a simple cubic lattice, one can very easily write a, b and c as a constant by n in the ax direction, in y direction and in the z direction, and one can construct the reciprocal vectors as very simply a dot b cross c in the following way. Now if one finds out b cross c is nothing but 2 pi times a square, and y cross z would become x cap, and a dot b cross c, a vector is nothing but a times x cap dot b cross c we have found in the numerator as a square x cap. If one solves it, a square in the numerator and a cube in the denominator turns out to be a in the denominator, and x cap dot x cap becomes 1. In the numerator we have unit vector x cap. So a in the reciprocal lattice becomes 2 pi times, there will be not dot here, 2 pi times x cap. So a constant term multiplied by again unit vector x cap. In the similar way one can find this will be again 2 pi times y cap, and c would be 2 pi a times z cap. So these are nothing but a scaled version of again a simple cubic lattice. So reciprocal lattice of a simple cubic is again simple cubic. So next question we have is, if one exploits all the symmetry in the simple cube, then the volume of the K space in the first Brillouin zone, in which we need. So this particular thing, let me come to the point, can be reduced down. In a simple cube, the volume of K space reduces down to volume of tetrahedron. Okay, now one can draw this tetrahedron in a way, because let me try to give you an analogy by a picture, and then I'll do the calculation as well. Now the reciprocal lattice of a simple cube is also simple cube. So the center point is 0, 0 point, one terms it as gamma. The corner point is our R point. We have other points as well. The edge center is M point, face center we have is X point, and also the lines connecting to these high symmetry points as well. Let's not go into that detail right now. So if one draws it and uses this particular tetrahedron, the volume of this tetrahedron is nothing but 1/48th times the volume of reciprocal cell, reciprocal unit cell. And volume of reciprocal unit cell is, we have found out, these are the unit vectors, primitive translation vectors for the volume in the reciprocal space. So A dot B cross C gives us the volume of the polyhedra, and B, and we have found out from above, it is 2 pi x cap times 2 pi A y cap cross 2 pi A z cap. This is the volume, and volume of the tetrahedron 1/48 comes in front. And if one does the math, then 2 and 2 becomes 8, which cancels with 48 as 1/6. A, pi by A, pi by and pi by A becomes pi by A cube, and y cross z is nothing but x cap, and x cap dot x cap is 1. So we have the volume of tetrahedron, that is the space, K space volume required to solve the eigenvalue problem, becomes 1/6 multiplied by pi by A cube. Now these the following questions in a present assignment are actually the thing to remember. For a simple cubic lattice, the gamma point has the coordinates. Now gamma point, as we now for a simple cubic lattice, gamma point is the most symmetric point, and therefore the coordinates are kx, ky, kz equal to 0. So for gamma point, kx is 0, ky is 0, and kz is 0. Okay, and for a simple cubic lattice, the R point in the first Brillouin zone has coordinates. Now let me just try to go here. Now we saw that R point, which was here at the corner of this connecting edges. Now if one chooses the coordinates judiciously, this corner I'll draw in this plane as well here. Gamma point, we found out is the center, we chose 0, 0, 0, and this part, so let's say there is an axis that goes in such a way, this way, and let's say this is pi by a, and this is pi by 2a. In fact, this becomes pi by a. Okay, this distance is also pi by a. Just a second, let me choose the coordinates. This point is nothing but R point. Now if one chooses this coordinate, so it comes out to be pi by a, and pi by a. Okay, one has to do the drawing in a systematic way. Let me just think for a while. I can figure it right now or not. Here. Okay, it can be done in this way. Consider these three faces and this face. Okay, there is a vector that goes here, and there are three directions I am marking. This is coming in this way. The length is pi by a, and this is pi by a. So this point is nothing but a part of this small cube over here. Okay, the length of whose each is pi by a, and therefore R point becomes diagonal vertex becomes pi by a, and pi by a. Next is M point. M point, as we have seen above in the picture, I'll draw again, is the corner point in this way. This we know gamma, this is we know as R. This is M point. Okay, so this M point was there, another was this direction. So this M point is actually lying only in a plane. So if I consider this as 0, 0, 0, M point, this M point is a part of this plane. Okay, so one of the coordinate of M would be 0 for sure, but which coordinate it will be 0? Now if I take it as Z direction, and let's say this as X and Y, so M would be pi by A, and Z is 0. This coordinate lying in the horizontal plane, this plane, the coordinates will be pi by, and this will be Kx, Ky, and Kz. So we have our option. Kx is pi by, and Kz is 0. X point we have seen from above picture as a midpoint of a face of the Brillouin zone. Gamma, we've seen M, and R point. This is X point. Now if I choose this plane, let's say as X, this one is Y, and this goes as Z. So X lies only on the X direction, and therefore we'll have coordinates pi by a distance, then 0 because it is on just an axis, pi by a 0 0 would be the coordinates for x point, and we have pi by 0 0. We have the following option as the correct option. Now the Kp perturbation Hamiltonian, next question is Kp perturbation Hamiltonian of a square lattice for kx pi by a, ky pi by a has symmetry similar to. Now if one draws this, let's say we have the square lattice, the center point is of course gamma point, and if I draw any vector, and now since we have to choose, let's say this is kx direction, ky, this point is pi by a, this again pi by a, this distance I'm talking about. This point is nothing but pi by comma pi by. So we are talking about this vector. Okay, so this vector due to the symmetry present in the square lattice can be flipped here, back, this. So and also so this the symmetry at this particular pi by point is similar to the gamma point, because this is, if I write gamma is 0 comma 0, then whatever the point this is, pi by comma pi by, this will also have the same symmetry as similar to, because the other point, which are x point and sigma point, will not hold the condition. So Kp perturbation term for a square lattice is similar with kx pi by a and ky pi by would be similar to a gamma point. Then we have our next question, that consider a two-dimensional square lattice. The ratio of kinetic energies at m point and x point in a free electron description is the following. So now if one thinks that there is a free electron, only one free electron, then energy of such a system, an electron would be given by h cross square k square by 2m. But now we are in two dimension. One extends this analogy in two dimension as follows: the k becomes kx square plus ky square, and we are given the following information, that there is an m point and an x point. For an m point, we have kx ky as pi by a comma pi by a, and for x point we have pi by a comma 0. So let us take the ratio of the kinetic energies. So if I say Em corresponding to the kinetic energy at m point and Ex at that, then it becomes h cross by 2m. Kx in this term would become pi by a square, and denominator we also have energy term corresponding to at x point, pi by a square plus 0. So now it is very simple to understand. H cross by 2m cancels with each other, and this becomes twice of the denominator. So Em would become twice of Ex is equal to 2. So the ratio would be root 2 1 by 2 1 by 2 n would be 2. Alright. The next question we have is the following: that consider a one-dimensional metal with atomic spacing A in the tight binding approximation with 1 electron per atom. The atomic functions are given as in the form psi r minus ri, where ri is the lattice translation vector. Assume further there are three given conditions: psi r minus ri, h psi r minus ri is minus of E naught, psi r minus ri, that is the interaction of a function with nearest, that if I draw the chain as follows: and if I say that this is the, let's say x is equal to 0, then Ri plus 1, or I should say if this is the ith atom, become I plus 1, and left become I minus 1. So if ith atom interacts with its nearest neighbor, then we have energy term costing as minus of V, and if this ith atom interacts with other wave functions for j greater than 2, this means that if this atom here interacts with this one or interacts with this one, there is no cost, energy term is 0. So these are the following condition given to us. Assume, and the option given us are this. So basically what the question wants to calculate the energy relation or energy dispersion for such a system. So I will start this as follows. Okay, so let us consider that I'll write some notations first of all. So we are given single electron per atom. Okay, now this single electron per atom, the Coulomb interaction between an electron at site R with some other nucleus site J, let's write as Vj equal to V of R minus Rj. Okay. Rj would be the difference between the electron at site R and site J. Now Hamiltonian for such a system, one can write kinetic energy plus potential energy. This is nothing but K plus summation of all those Coulomb interactions which the electron at site R feels with the other nucleus of other nuclei. So this is nothing but summation of all interactions of electron at position R with nuclei at J. J is just an index, I should be careful. Now if one finds out, if works on the, let's say the wave function m of the electron, finds out the energies corresponding to it, this comes out to be J working on wave function m. I can write it as Km and sigma Vj working on a summed over all j's. So if I pull out Vm out and say that, now in this condition I've just pulled out that if the electron is on the mth site, this term, the potential energy Coulomb term, I have pulled out, and this is the summation of the Coulomb interaction which the electron feels other than the nuclei at the mth site. Okay. So this, or if I write in a neat way, this becomes K plus Vm working on m. This K plus Vm is nothing but the Hamiltonian, if there were single nucleus, that is mth nucleus. Okay. Now if I write this k plus Vm, which is Hamiltonian for the electron if there was single nucleus, I can write this as this part. I'll pull it down, working on m, as an eigenvalue equation where I get atomic energies. So K becomes the kinetic energy of electron present on mth nucleus, and Vm is the potential energy that fields due to the nucleus, and E atomic is the total energy. Now what we have is a series of nuclei. Okay. So we assume another thing that we assume in this situation is that the nth site, this is a boundary condition, the nth site, the conditions at nth site are similar to condition at 0th site. Okay. And we use that all the orbitals present, all the electron orbitals, because we have one electron per atom, and we assume that all these orbitals are orthogonal to each other. So if I try to calculate this bracket, I would have a delta function, delta of nm, where it will be 1 if nm is same. Okay. Now to solve the Hamiltonian that we wrote earlier, the earlier version of this Hamiltonian, this is our main thing, because now we have to figure out what this means. Okay. Now to solve this Hamiltonian, let's take a trial function. We'll go this problem by variational principle, in which we assume a trial function. Okay. Trial function which is a linear combination of all those atomic orbital functions. Okay, this is a trial function, and the effective Schrödinger equation can be written down as summation HNM, working on phi m, E phi m, where HNM is the matrix element, okay. Now what we know from above is this part we have figured out earlier, which was nothing but this working on let me write it down from the above, Km Vmm, or in fact I can write this here, atomic times m plus summation Vjm plus summation j not equal to m Vj working on m. Now if I solve this, I have E atomic, the delta function comes in, and plus summation j not equal to m n Vj and n. So this is the condition that is given to us in the question, that the interaction of nearest neighbor, interaction of these atoms with nearest neighbor as minus of E naught if n is equal to m, minus of v if n is equal to m plus minus 1 for the left and right side, and 0 if otherwise, or 1 is going down the farthest neighbor or the second nearest neighbor, then it becomes 0. So it simplifies to, for this first term is for if the electrons, if there were only one nuclei, and then we have interaction term, which becomes minus of v with the delta function n plus 1 comma m, and again a minus of v if there's a delta function n minus 1 and m, and a final term if n is equal to m, we have a final term E naught. Now this constant term E naught can be merged with this E naught with delta nm. This delta E naught and atomic can be clubbed together, and let me write it as naught or with a minus sign, delta nm minus v sign delta n plus 1 m minus delta n minus 1 comma m. Okay, so this is the Hamiltonian that we have, the matrix element we have solved, H and M. Okay, this H and M, if the Hamiltonian we have figured out. Now let us plug this Hamiltonian H and M is this thing. Now if we plug it, H and M, this should be the equation, equal to this is nothing but a constant term. Let me call it some number epsilon naught. Now phi m is a trial wave function, and let us assume it to be some sort of exponential type. Let's say e power minus k n a, because we are in one direction only, and I'll have a normalization term because of orthogonality. This is for the first term, and then we have v times e to the power minus I k n plus 1 a divided by root n, plus, because if I've taken out minus v, so it should be plus e to the power minus k n minus 1 a divided by root n. Fine. And this should be equal to E phi m, phi m which we have assumed it to be the of the due to variational principle. I have said to the power minus I k n a by root n. Let me take a variational page. So if I cancel phi e to the power I k n a from the right hand side left from this, and from if I pull out I k n a from here and I k n a from here, I end up with comparing the energies as epsilon naught minus v times e to the power minus I k a plus e to the power minus I e to the power plus of I k a. Alright, Because if I multiply divide by 2, this expression is for cosine function, so minus 2v cos Ka. This is the energy dispersion for tight binding model in one dimension, where epsilon naught is the term that accounts for the all the interactions the atom has with if there were no other nuclei present, plus an additional term, that is E naught term that arose from the condition n is equal to m, and the next term is for the potential energy term 2v cos Ka. And what it does is the following: if one plots E minus, if it from shifts E minus epsilon naught on the y-axis and K here. Okay, so let me just put A here, because these are the lattice points I'm talking about. If A is 0, I'm talking about this, then I have minus of 2v, minus 2v here, this is minus c. So this function would be going in this fashion. Okay. This is our expression for the following energy dispersion. So we have E is equal to epsilon naught minus 2v cos Ka. Now the symbols can be written down differently as per the notation. So for our present question, which said for a one-dimensional metal with atomic spacing A in the tight binding approximation with 1 electron per atom, and given these three conditions to us, the energy dispersion we found out was E naught minus 2v cos Ka. Okay. Now we are left with the final question. Now this one again, the 17th question is again a bit tricky question, which I have not accounted for it yet. It says that the crystal potential of two-dimensional square lattice with spacing A is given by Vx is 2V naught cos 2 pi x by A and cos 2 pi y by A, which is nothing but of this form. In the x direction it goes as this, and in the y direction also goes as this, and therefore one would have some dips and some minima as well in this two-dimensional plane. Okay. Now if one has such a potential, then the approximate band gap given to us at the x point is. So if now this problem is I have not solved it yet, but I can give you a lead. If one solves this problem in the model of chronic penny model, where one assumes that the potential due to these nuclei present goes as this way, right? And so chronic penny model assumes these potential to be rectangular potentials, right? Now after if one solves this particular assuming the chronic penny relation and finds the energy gap in this particular problem, but finds it is of the form of let's say whatever the height that I have used here, let's say V. So the energy gap between the between the solutions found is V, and if one takes this problem to be of this kind, which is a cosine wave moving in only one direction, then it becomes the coefficient of the cosine wave. Let's say if I have a potential, let's say just for the time being 2v times cos of 2 pi x by A, and let's say this is our x direction, then the energy gap we have becomes the coefficient of this cosine term is 2v. Now in the same analogy, one can write as the following, as 2v cosine 2 pi x by A plus cosine 2 pi y by A. Now we have square lattice, so A and B are equal. Now using the same analogy, we can think it of that the coefficient is 2v, so it will be 2v. I will approach this particular problem in more rigorous way, where I will solve it for you for a I'll show it how it is done for in one-dimensional model for a chronic in one-dimensional situation for a chronic pain model, and also for how one can extend this analogy to 2 dimension, and we'll see rigorously how it turns out to be 2v naught, because I've tried solving it in this perspective, but I only was able to find analogies which said in this way. So the approximate band gap would be twice of v naught. Okay, for right now I cannot provide much more rigorous detail to this question. Okay, so that is how we have finished our present assignment solutions. So if you have not understood any point in this particular live session, you can unmute yourself.
Thank you, sir.
Actually, I have another question. The lectures of this week 6 and week 7 are, I think they're too difficult. Just week 7, I just can't understand anything else. So, I mean, how is there any suggestion that can help the deductions and whatever the SAN has done? Those are, I mean, beyond the limit. Can you suggest anything which
Um,
help
so
to
this
augmented
would
and
be
informations?
I agree because week 6 and week 7 lectures are more focused on theoretical approach mostly, that how these things are done, because nowadays these energy calculations are done in DFT. So what one uses the software called WASP, and that software has the how that particular WASP program, uh, the inbuilts of the WASP programs are embedded in those lectures for in week 6 and week 7. I'll for sure try to make the solutions much easy in a much I cannot promise that, but I'll try to boil it down to a digestible way, that how to approach those problems in for week 6 and week 7 for sure. And also I have left out 2 problems for today as well. I'll also cover it up
Yeah.
in the next part.
The problems are not that exhaustive. The
Yeah.
lectures are very
Okay.
okay.
Okay, I understand. I get it.
Okay, thank you.
Okay, so thank you both of the attendees to join this session. I will close the session right now, and then we will meet on next Tuesday with the assignment solutions for week 6. So
Okay.
thank you, and see you in next lecture.